Hello, my name is Brindyn Schultz. I am a sophomore student at Lewis University studying computer engineering, computer science, and mathematics. And today I am showing my most recent project, the PIP-1. I started this project on the 14th and I finished it on the 28th. And first off, a little bit about the computer. The PIP-1 was a theoretical educational computer designed by Forrest M. Mims III in his book Understanding Digital Computers, which was published by Radio Shack. The computer was designed to teach people how digital computers work at the lowest level. The computer is an 8-bit machine that follows the typical von Neumann computer architecture. And I want to give a special thanks to Myzuma Games for his video about serial data in Minecraft, Amworth for his video on compact full adders in Minecraft, and then I found an anonymous online thing about compact D flip-flops in Minecraft, and then Proper English 19, who had a video on binary counters. So I'll go over the inside of the computer before I show it running the program. The color coding in blue, you will find the input and output. This will include the 16:8 input on this front panel here, as well as it will include the start and stop buttons up there. It has the on-off switch and the busy light over there, and the readout, which is going to be your output up there at the top. And then this will feed into the prom, the program, and the program counter, which are going to be in green. The clock will be in this light gray color. The address data bus will be white. The arithmetic and logic unit will be in yellow. All the registers, the memory address register, instruction register, and the ABC registers will all be in red. And the control unit and control bus will be in pink. So I'll actually fly over there and show you the inside of the computer. So here are where you can interact with the on-off switch, the start-stop button, and the busy light will come on when the program is running. And over here is the 16:8 input for the from the device panel to take it to prom, which is right here in green. And when you hit start of the machine, it'll automatically update the input from the panel to prom. And if you were to accidentally hit a switch while the program was running, you wouldn't break anything unless you had flipped a bunch of switches and then went and hit start again while the program was already running. And then you have right here, this red part here is the memory address register, and this works in conjunction with the control unit. So when it gets a signal, the memory address register will select the location that it needs to from the data it receives from the serial and data bus, which will select a line from prom here and send it to the address and data bus in serial, which is here. And then this data is shifted downwards and then split from serial to parallel and then taken from parallel buses to other components of the computer where it may be used. And here is the A register on top, this red part here. And on bottom is the B register here. Here is actually a mirrored copy of the A register. This will make it a lot more compact for when I want to send stuff from the A register to the C register. And then this small little area here is actually the C register, and it will not take things from this A register copy and put it into the C register into the C register unless it receives an input from the control unit to do so. And it will be taken through these blue buses here in parallel across the computer to the readout. And then attached to these registers, you can see here we have, this is the arithmetic and logic unit in yellow. And by default, it is in subtraction mode. But if the control unit gives a signal here, it will toggle the arithmetic and logic unit to go from subtraction mode to addition mode. And this has the ability to carry over, and it does have a carry flag if needed. And if the control unit sends a signal to do so, it will actually send data from this ALU via right here. It will send data from the ALU to the A register right there, so you can keep performing operations using this ALU. It is a combinational circuit. It's one of the only combinational components in this whole computer. And right here is the instruction register. it will take info from the address and data bus, run through it. It'll only look at the opcodes. It doesn't actually need the data. And depending on what opcode is entered, it will fill out the control register here. And over here in light gray is the clock, and it will increment clock cycles. And so this will be clock cycle 0 all the way up to 5. There's 6 clock cycles here. I do have 2 clock cycles that don't do anything. They're just buffer clock cycles to allow the computer to settle. That way you don't have glitches related to lag and performance problems if you're running a PC that's like mine is not too great. And then here is the serial bus for the control unit. You'll see it's actually double the size of the address and data bus. It has 16 bits instead of 8 bits. And then it will move the signals and use them throughout the computer as needed. And I believe that that is this entire computer from the inside. So you don't actually need to do anything back here. All you need to do is put in your machine code here, which I already have a program pre-selected here that I've run. This is actually what the readout will be when the program is finished executing. This is a very tough program for the machine to run. It takes a while to run. It uses every single macro code possible. It's not very easy on the hardware, but the computer can do it, and it can do it very well. So you put in your code, you hit start. As long as the machine is on, it will actually start the machine, and the busy light will come on, and it'll run through everything. And when it's done, it will stop the clock automatically. The busy light will come off, and you'll get your readout. So now that we've seen all this, what are these opcodes so that you can program it? Well, all zeros is going to be a clear. Zeros and a 1 is going to be load the accumulator. 0010 is add, so you're going to specify which location on the panel to take that data and add it to whatever's in the accumulator. You got to subtract, which is the same thing as add, but it subtracts instead of addition. You have a jump, which can jump over, say, lines of data or something. So you can jump. I actually have one in this program. I have here, it jumps from line 4 down to line 8. And that's because lines 5, 6, and 7 are just data. So I don't want the computer to execute these as if they were program code. And I have a few more. There's out, which will take whatever's in the A register, move it to the C register, and the C register is directly linked with the readout, so that'll be your output. I also have a NOP, which is no operation. It just lets a clock cycle pass. It doesn't do anything. And then you have a halt, which turns off the clock and ends the program from running. It does the same thing as if you were to press the stop button manually, but obviously I don't want to have to hit the stop button every single time I run a program. So this will turn off the clock when I have a halt in my program. So let's look at this program here and see what it does. First, it's going to clear the computer. It'll clear the A register, B register, and C register. And then after that, it's going to load the accumulator with whatever is in PRAD byte 5, which is down here. You can see this is the number in PRAD byte 5 here. It's in binary, obviously. The whole computer runs on binary. There's no decimal inputs or anything. And then it will move on to line 2, which will say to add whatever's in PRAD byte 6 to the number that's stored in the accumulator. So this will get stored in the B register, and then it will add the B register in the A register and store that result in the A register. After that, I have a subtract, and I'm going to subtract whatever is in line 7, which is down here. So I'm going to take this data and subtract it from the result from when I added those two. And then after that, I have a jump, and so it's going to jump to line 8, which is all the way down here. and then I just have a no operation, so nothing's going to happen. And then I have an output, so the out command is just going to update the A register and copy it over to the C register, which is going to show the output, which after it does the addition and subtraction, the output should be 15. And then it's going to halt. So it's going to turn off the clock and turn off the busy light, and that'll be the entire program. So you actually do have 16 lines of program you can use. This program actually uses 11. So I do have 5 more lines of program I could use. But there's not really too much I could do with that. I could just add more addition and subtraction if I wanted to. However, the longer your program, the longer it will take to execute. So do keep that in mind. And this is actually, well, a very educational version of the educational computer. So the computer that was theorized by Mr. Mims over here, Mr. Forrest M. Mims III, he theorized that this computer should run fast in nanoseconds. But in this implementation of Minecraft, you could see everything happening in a slower pace, and you could follow each of the micro instructions as it happens around the computer. And so a program like this, when I hit start, is going to take probably 10 minutes to execute from start to finish. So let's just watch it happen, why don't we? So let me switch so that I can interact with this button. And I'll switch back, and you can see what's happening. It's going to be laggy because I'm recording, and the recording software lags up my computer quite a bit. So this is going to reset the program counter right here. This is the program counter. I believe it already reset, and the clock is running. So when this clock pulse comes back around here, it's going to update this. And now we should have our first micro instruction for the cleared running. So it's going to read what's in the program counter, which we can watch it. Right now there's a 0 in the program counter. And so I updated to a 0, and then it's going to read from the memory address register location in 0, which is also going to be a 0. So it's going to update again, and we'll have another 0. Okay, and now we get to watch the instruction register is going to change to include the instruction set for clear. And there it goes. It just updated the instructions. So now we get to wait. And on the next clock pulse, it's going to send a signal to increment the program counter, which there it was. So if I come down here, I can see that in a second it's going to increment the program counter. There it was. So now I get to wait for the next signal, which is going to update the A, B, and C registers. It's just going to clear them. So now if we come over here to the A, B, and C registers over here, we can watch them clear, and it's actually going to look very cool. It'll take a second though. And there they go, they're clearing. And everything is now set back to 0. So now if we come back to the clock pulse, that was it for the macro instruction for clear. So the next macro instruction that will be run, when this cycles back through, I'll have a little bit so I can explain some other things. The next macro instruction that's going to run is load the accumulator, and we're going to, as I explained earlier, we're going to load the accumulator with what's stored on prom line 5. And it's going to, so all that's going to do is it's going to take that data from 5 and send it to the A register. And you'll see how the computer does this. It's just got to cycle through. Like I said, I have some buffer clock pulses. There's actually 2 more after this, where it's not going to do anything. And it's just so that lag can settle and the computer can kind of settle down, so you don't have things breaking if you're running on a computer that's not great like mine. I would love to get a newer computer that can run more complex stuff like this while we're recording. But I don't have the financial resources for that at the moment, especially in 2021. with the pandemic and the chip shortage, it's hard to get it to be able to afford a new computer. Anyway, on this next clock pulse, when this cycles back around, we'll start the macro instruction for load the accumulator. And there it goes. So if we come back over to this address and data bus here, it's going to read from the program counter, which since it incremented, it's now going to read a 1. And there it is. And now it's going to select line 1 from the memory address register and take that out of prom. And here that comes. So this is what it loaded. And so now it's going to update the instruction register, which I already showed. And then after that, it's going to increment the program counter. And then it's going to read from memory address 5. You can see 4 plus 1 is 5. So it's going to do memory address register location 5 from prom and send that up to the data bus. I'll actually check where the program is right about now. So it just incremented the program counter. So it's going to actually update that on this next clock pulse when that comes in. So we can wait for the clock pulse to come in. And there it is. So if we come up to the address and data bus here, and we wait a second, it's going to take the data from address line 5 and prom and update that into the address and data bus here. And there it goes. And now if we drop down below on the next clock cycle, it's going to write that data from the address and data bus to the A register here. And there it is. You can see it copied it over. And so now we can go back to the clock cycle, and that's it for load the accumulator. So the next line that will run is going to be adding. We're going to add the byte. We're going to add the data from pred byte 6. So it's going to be pretty similar, you'll see, but there will be some slight differences. It's just got to run through these, like I said, these buffer clock pulses to let everything settle, kind of calm down for my laggy computer. And also, I'm going to upload this video on YouTube, and I will give a Google Drive link with the download for this world so that you can play with it and program your own things, and you can write your own programs. You can modify the hardware inside of here, try to make improvements on it. Anyways, it's about to hit this next clock pulse, which means the add macro instruction will start. So here comes the clock. It just updated the clock. So if I come to the address and data bus here, it's going to read from the program counter, which should give a 2, and there it is. And then it's going to read address line 2 out of the prom and put that into the into the address and data bus here, which it did. And now it's going to write that to the instruction register like it did before. And then it's going to increment the program counter. So the program counter will have 3. And then it's going to write whatever's in prom line 6. 4 plus 2 is 6. It's going to write whatever's in prom line 6 to the address data bus here. And then it will update the B register, and then it's going to perform addition in the ALU, and then take what's in the ALU and send it to the accumulator. So it just incremented the program counter, and when it switches over, it should be writing that data from prom line 6. So we can look here. So the pred byte 6, which is on prom line 6, is going to update to this memory address register. We'll see it come in soon. And here's the data. And now it's got that. On the next clock pulse, it's going to update that to the B register, which is down here, right below the A register. It is a bit hard to see the B register, and I apologize for that. But yeah, if you come down here, you'll see the data come in, and here it is. And then on the next clock pulse, it's going to change this from subtraction, because right now it's in subtraction mode. It'll change it to addition mode. And then while it's in addition mode, it'll happen almost instantly. Right after it switches to addition, it's going to store that result and send it to the A register, which it just did. And so now that result that is 40 is stored in the A register. And then, so now we can go to the next clock pulse, and that was the add macro instruction. And so it's actually pretty close to giving the next command. So I also wanted to take the time to say that this is a pretty tentative build. I came up with a lot of this hardware myself, almost all of it, to be honest. And the parts that I didn't quite come up with were modified from other people's designs. But I would say 90% of this computer was completely original. Nobody had ever made anything like this. And the actual computer itself, the PIP-1, was never built, not even in real life. Nobody's ever built the PIP-1. So as far as I know, I'm the first person who's ever attempted that. Anyway, this is starting the macro instruction for subtraction. So we're going to see the program counter is going to read what's in the program counter, and it's going to give that 3, like I said, and then it's going to select 3 from the prom line. And sure enough, that was what was in prom line 3. So it's going to take what's in the 7, pred byte 7, so prom line 7, and it's going to update that to this data bus here. And then it's going to send that to the B register, and it's going to, since it's already by default in subtraction mode, it's just going to send that result to the A register. And right about now, it should have already updated the instruction set, and it should be incrementing the program counter, which it just did increment the program counter. So now the program counter is at 4. And after this clock pulse, it's going to write the data from prom line 7 to the address and data bus up here. So we'll get to watch that happen. I apologize, but this part does take a bit. It's just for safety reasons. If I'm trying to make it go any quicker, you might have data merging. So that stored that there, and now it's going to take that result on the next clock pulse and put it in the B register. I might be too late to watch it happen. Hopefully I'm in time. Okay, I was just in time. And now that's going to perform subtraction, and any minute now it's going to store that into the A register, which will wrap up the subtraction part of this program. Should be updating that right about now. There it goes. So it stored it into the A register, as we see here, and then that's it for the subtraction macro instruction. So now if we come back up to our clock and for our control unit here, we gotta wait another 2 clock cycles. It's going to perform a jump next, because if you remember from the program I showed, we had those data lines, and we don't want those to execute as normal instructions and normal code. So we want to jump down to line 8 in the program so that we can have our no operation, our out, and then our halt. And so when this clock pulse comes around, we'll start the macro instruction for jump. And there it updated. So if I come over here, it's going to send a 4 from the program counter, because that's what the programmer's counter is currently set to. There it is. And then it's going to select from prom line 4, which is going to give our command for jump, and it's going to say jump to line 8. So if we come down now, it's going to update the instructions. We might be able to see this in time. Oops, sorry. And there it's updated the instructions for the jump. On the next line, it's not going to increment the program counter like it has been, but rather it's going to set the program counter to 8, which is going to be really cool to watch. So in a little bit, you're going to see it. It's going to reset everything and then quickly set it to 8 before the program could continue running. So you'll just have to give it a second. Actually, I apologize. On this clock pulse, sorry, that was a bit louder than I expected. But there you go. You can see it set the program counter to 8. And that is everything for the jump command. So now we just got to wait for a few clock pulses because it's such a short command, such a short macro instruction, so it doesn't have a lot of micro instructions. So we have to wait 4 clock cycles of nothing before it executes the next macro instruction. And the reason it took so long to update the program counter down there was because I had accidentally forgot that when you get 4, when you get binary 0 and 0 and a 1 here, that doesn't do anything for jump. Normally that would increment the program counter for any other macro instruction, but for jump, it doesn't do anything. Once it hits 1, 0, 1, that's when it triggers the command down here to set the program counter to 8. Or it'll just set it to whatever you put in the address line. But for our program, it's there's an 8 in the address line, so it set the program counter to 8. Anyway, we're about to start the macro instruction when this clock pulse comes through for no operation. It's admittedly a very boring one, but it's important that you have a no operation. It's very fundamental. So this is going to read from the program counter. It should read an 8. And there we go. And that's because the program counter was set to 8. And then it's going to select from prom line 8, which is going to give us our instructions for no operation, which it just did. So now we can see the instruction set is actually going to change. The instruction register here is going to update the control unit instructions, which we'll see. And it just updated it. And now on the next line, it's going to increment the program counter. So we'll get to watch that. So if I come down here, it's going to increment this. So it'll increase the program counter to 9, which it just did. And we can now come up here, and for a no operation, that's actually it. So we just have to wait for a while, quite a while actually, because this is the shortest macro instruction in terms of how many macro instruction sequences it is. The only other shorter one is a halt, but obviously you don't have to wait for a halt because the clock will stop. So when you have a no operation, it's kind of just sitting here waiting and waiting and waiting until your next instruction can execute. So I might as well show the extra parts here. As you can see, the readout cleared from when we had a clear command. I showed that from the inside of the computer, but here it is from the outside of the computer. We can see the readout's completely gone. The busy light is still on because the program's still running, and start and stop, we can't really do anything with that. If I flick that lever, it'll turn it off. That won't stop the machine from running the program. That'll just make it so that if I hit start and stop, nothing happens. And so we're right here at the no operation on line 8, and it's going to run next the out and then the halt. So if we look where we're at, we still got a little bit, so I could get a better look at that. So it's almost done with the no operation here, and then it's going to run the next one, which is going to be the out, which is going to put what's in the A register, which is currently 15, to the C register, which is directly linked to the readout. And then here it's going to stop the clock with the halt. So let's see where we are. Okay, on the next clock pulse, which should be coming in soon, it's going to start the macro instruction for out. So there it went. So we're going to start by, again, reading from the program counter, which is going to read a 9, because that's what's currently in the program counter. Sure enough, it read a 9, and now it's going to select from prom line 9, which has the program code for out, as you can see here. So now we can see, if I come over here in time, we'll also be able to see the instruction register update the control unit. Looks like it's doing it. Yep, it's doing it. So this isn't too exciting of a instruction set, but it'll be cool to watch. So on this next, there it goes. We're going to, again, increment the program counter. This will be the final one, because for the halt command, you do not increment the program counter. So now we ticked the program counter up to 10. And then we're going to next, we're going to write to the C register. So if I come over here really quickly, hopefully in time, we can see the C register update. And there it goes. So that just updated the C register, which is going to take this data up here. And let's see if I can run faster than the lines can carry. No, I cannot. So it put the readout here, but you'll see the busy light is still on. That's because the clock hasn't stopped yet. So that's it for the out macro instruction. It's another short macro instruction, so we're going to have to wait a few clock cycles before starting the next macro instruction, which, as you saw, we had a 10 in the program counter. So it's going to read program line 10, which it has the halt command here. And that will stop the clock. It's going to give a second for everything to settle. That's why I have all this delay here. It's gonna wait about 10 seconds after the clock stops and turn off the busy light. That way everything settles, and that'll be it for this program. I have tested this with many different programs, and as far as I know, as long as all your syntax is right, you know how to write the programs correctly, it will work with any program. There is a glitch that I have not been able to fix yet. I believe it is a Minecraft glitch and not a fault in my hardware. I will try to figure out a way to fix it, but at the moment, I've only been able to make it less and less common for the glitch to occur. And it only occurs if you are trying to run 8-bit data lines. So here we are now starting the macro instruction for halt. So it's going to bring a 10 from the program counter up here. And there it is, that's binary 10. We've got 8 plus 2 is 10. And it's got to select prom line 10, and it just did, and that's the halt command there. So now we can see the instruction register update to include the halt instructions. And there it all goes, it updated. And on this next clock pulse here, it's actually not going to increment the program counter, but instead it's going to send a signal here to stop the clock. We'll be able to see it here in a second. There it goes, it stopped the clock, and now you can see this is counting down before it turns off the busy light. So in a second, we'll see this busy light turn off, and there it goes. And that was our entire program from start to finish. And sure enough, it took about 10 minutes, like I said. So yeah, that's about all. If you like this, feel free to share it. It took me quite a bit of work. Minecraft has a statistic I can actually view about how long it's taken. I spent 2 days, exactly 2 days, with this world open. So about over 50 hours. So that's about all. Like I said, I'll have a world download so that you can download this world and play it yourself and write different programs or even modify it. If you can find a way to make it better, that'd be awesome. I would love to see it. I'm actually pretty impressed with myself that I managed to build this in exactly 2 weeks. And I do suggest that if you are into computer engineering and you like building computers and projects and stuff, Minecraft is a brilliant simulation for simulating hardware. I don't think there's a simulation that can simulate hardware in a more visual way than Minecraft. Um, so I do suggest that you use it for projects and that you build a computer uh, of your own. Uh, you don't have to design the computer. Like I didn't really design the overview of this computer. I did design how it would work in Minecraft, but that's about all. So thank you. Again, this was Brindyn Schultz, sophomore student at Lewis University, studying computer engineering, computer science, and mathematics. And I'm signing off. Thank you.